So we just take this index here, j, to represent each person j in the classroom. And we sum over all of the ages of everybody in the classroom, excluding person I, and then we divide by 1 over n minus 1. Okay, this average characteristics here. Because we want to get the peer effect. We want to say, are you asking why is it j and not I?
No, I was just.
Go for it, please ask.
I was just asking what you actually said. But,
Oh, so x minus ij is the average group characteristic of everyone excluding person I. So you can put this in the average group characteristic in the class of everyone excluding person I, right? My apologies for like not having the sentence like fully written out. Question?
Is that a comma in between the J and the C?
It can be.
No, down at the bottom.
Where? Yes, this
Okay.
is XJC, right? So this is person J, classroom C. And the reason why I use a different index here is because we're specifically talking about the outcome for person I. So when we sum over the average characteristics of everybody in the class, we want to say let's sum over everybody excluding person I. Does that make sense? Okay. So we want to say how does the average class or the average number of women in the class, what's the average number of women in the class? These are going to be, what kind of effects are these going to be? Which one of these effects are the X is going to be captured? Say it again.
Exogenous.
Exactly, the exogenous or the contextual effects. Like, do students tend to do better in classes where there are more women, for example?
Why is student I excluded though?
So we want to think about the peer effects. And if we included student I's characteristic, then that's just going to be how student I's own attributes are going to be affected.
Okay.
Yeah.
So does that mean this model is always exogenous, or in any case you're saying?
No, we haven't finished yet. We haven't finished yet. Good question. Okay. Then the next thing that we're going to add is beta 2 y bar minus I comma c. Right? And what's this going to be? You can tell me, you can guess what this is. What's y bar minus I comma c? You know what x bar minus I comma c is. So what's this? What's y bar I comma c going to be? Come on. Don't be afraid. The average what? The average of what? So this is y bar. So it's the average of what? It's on the board. Say it again. Exactly, it's going to be the average outcome of all of your peers, right? So this is going to be like, what are the grades that everybody else is getting on the test? So if you know that this is a test where everybody's going to crush it and they're going to get a 90, what score are you going to aim for? Are you going to aim for like a 5%? No. But if you know that this is a test where everyone's going to get like a 30%, and you're like, look, if I get a 40, like I'm good, right? So that's what you think about it. And so then this is the average score. This is the average performance of peers, right? Okay. Plus epsilon IC. And what's this epsilon into here? The error term, which is going to capture what? This is the error term. So this is going to be like everything that's not explained by myself. Yeah. And we can also add to this. Let me erase this. My apologies for this. We can add a term that is a control that takes into account like classroom effects. So like, is it a classroom with windows, for example? Is it a classroom that has white paint on the wall overhead? What's the epsilon S? These would be features of the classroom, or who the teacher is. Right? So this is like features of the classroom. This is like a classroom fixed effect. So what is something else that can go into that classroom fixed effect? Well, it's specific to the classroom.
Technology in the classroom.
The technology in the classroom, like, was it well lit? Because if, for example, I did this number during a test, what would happen to performance? Right, it could change, right? And it has nothing to do with the fact that, and we would see that everybody in the classroom did really poorly, and we would say, oh, they did poorly because the other person did poorly. And it's like, no, they didn't do poorly because the other person did poorly. They did poorly because somebody turned on the lights. And so what kind of effect would this be in the context of this framework here? Uh-huh. Exactly, it would be these correlated effects. So everybody see the mapping here? So these exogenous effects are like the x bar minus IC. This is the y bar minus IC. And this is like the IC. Mapping from this model of peer effects onto these things here. Are there any questions so far? Okay, so like just to kind of bring it back, so we hypothesize that an individual's actions could be influenced by their peers and their environment, right? So we have this researcher that's at the door, and he just sees that, look, like all of these people seem to be doing really well, their test scores are positively correlated or they're negatively correlated. We want to understand why. And it can either be, well, there's just something about this context, and there's something about that. It could be they're really benchmarking relative to one another. This class is more from the curve. Or it could be there's something with the actual classroom itself. And we need to know these because they're going to be very different policy implications, right? If it was something about the classroom, the lights in the classroom just randomly go off, then what we need to do is fix the lights. Right? If it's the fact that students are benchmarking relative to each other, then it could be a situation where you set a really high bar and you say, look, we're gonna curve it and we're gonna set the median to be a bluff. And the higher we set that bar, that's gonna endogenously cost, like if I set the bar to a 95 for an A and like a 90 for a B, which it's not in this class, right? Then everyone's like, oh my God, like I have to get at this grade, and if I don't get this grade, I'm not gonna get this. And then all of a sudden, everyone starts to work harder because like my peers are working hard, and if I don't work harder, I'm gonna really get, I'm gonna get it handed to me. So you can set like these high expectations, and this is gonna endogenously create competition that can lead to higher performance. Okay. So let me just stop there and ask if there are any questions. Okay. Now, we want to get causal estimates, and the big thing that we're going to be fighting against is if these x's are correlated with the epsilons, we're not going to be able to get a causal interpretation of the big one. If the y's are correlated with the epsilons, we're not going to get a causal interpretation of that. If these IC's are correlated with that, also we're not going to get a causal interpretation. So let's just stop for a moment, and let's think about these things. Are these x's going to be correlated with these epsilons by construction? Who wants to take a stab at that? Like, are the x's of the people going to change in response to these things that we don't observe? Like, is someone's gender going to change in response to whether or not they have a cold that day? Because these epsilons are the things that the researcher doesn't observe that affects performance. So let's say somebody has a cold on that day, or they're sick. Is their gender going to change because they have a cold? No, right? And so by assumption, these x's are going to be exogenous, right? Or whenever you're in a regression, like we always want to make sure like the exogenous parameters we can identify what the coefficients are in them. Okay. Now, what about these y's? Are they going to be correlated with these epsilons? In general. Why not?
Is it because student is excluded from that?
Okay, so student I is excluded. So okay, so what you're saying is, and that's a part of the reason why we exclude. So student I's performance is excluded. So then the average performance of everybody else you're arguing should not depend on this thing that affects student I's performance. But what about student 2 performance? Is student J's performance affected by student I's performance?
Maybe.
Right. So in a sense, student I's performance depends on student J's performance, and student J's performance depends on student I's performance. And so even though we've taken out the mean, we've taken out student I directly, there's this indirect effect or this feedback loop that's happening here. And so we still have to deal with that. And so this is potentially endogenous. And how did we deal with endogeneity? You want me to look at other terms to see that? What do we need if we have an endogenous regressive? What do we need? I heard it. It was on the midterm. Don't be shy.
Instrument variable?
Yeah, we need an instrumental variable. And an instrumental variable in this case is going to be correlated with what, but uncorrelated with what?
Needs to be uncorrelated with the error term. Needs
Uh-huh.
to be correlated with what is it? The endogenous variable?
Exactly. So we need something. So I want to make sure that I give you enough time to talk about the paper. Okay. All right. So we're going to need something that's correlated with the average class performance of everybody excluding you, but that's uncorrelated with the error term, right? And so, for example, if we have some previous measure of student ability, that could be a possible instrument, right? Because you can think about the student as having a baseline level of intelligence. And if we know what their SAT scores or something like that, people with higher SAT scores are generally going to score higher on the test. So that's going to be correlated with this, but it's not going to have the same kind of a feedback point because the SAT score is not what is it's not the performance that we're going to be getting here. Okay. Now, let's see. Okay. Now let me just I'm just going to put up a couple models of these peer effects, and then we turn it over to Shannon so she can talk about the paper. Okay. All right. So this model is linear, but in general, like the models don't need to be linear. One of the difficulties with the linear model is if we did something that altered, that redistributed students from one class to the next, we're going to increase them in somewhere, but we're going to decrease them in somewhere else. And so in these linear models, it's like you can't do anything better for one group of people without hurting another group of people. But if we have a nonlinear model where, for example, like if you the performance, for example, of the class depends on the best student in the class. Well, if we take all the great students and disperse them across a ton of different classes, we could actually get like all of the classes being better because this is like nonlinear. It only depends on like one person. It doesn't depend on just. Okay, so let's look at some nonlinear models of nonlinear, and then I'm going to try to go to Shannon. Models of peer effects. So it's like, we have 50 minutes. Shannon, would you mind us going through the paper that you're going to present in next class?
Sure.
So we'll do that next class, and then we'll do all of the papers that we present next class. So that way I won't rush through this, but I'll take my time in setting this up, and that'll give the people who did not read the first one for this class an opportunity to read on Thursday. Okay? So I'll just take the remaining time and work through this. My apologies for that, Shannon. But I really want to make sure that we get a very solid foundation of this, because peer effects are all around you. Okay. So now that we've claimed that 15 minutes of time, what I'm going to do is I'm just going to write up what I said about the instruments, and then I'm going to talk about the models, okay? All right. So, the endogeneity concerns. So let's go. By assumption, x's are exogenous. So check the problem there. The y bar minus IC. This is endogenous because actions of I's peers, the action of I influences the action of I's peers. So we got like a feedback loop. So we need instrumental variables. So for example, measure of past performance. And especially and so one example of this will be, so there's a paper by Carolyn Hawksby. So in Hawksby, and I believe, Shannon, this is on the, in the files, right?
I'll double check.
Okay. So Hawksby and Weingart, 2005, what they do is they use the test scores of students that transferred in. As an IV. An IV means instrumental variable.
Can you like pause for a minute while I
Yes.
write this? And also, what does the title say?
Endogeneity concerns. Yeah. So this is just writing out what we said. So by construction, and then let me, just a moment. And then for 3, for IC, we can randomly assign this. So this is something like classroom size, right? We can randomly assign this. For example, in the STAR experiment, which we covered last class, classroom size is randomly assigned. Let me stop for a moment there. Let everybody catch their bearings. Any questions on what we've done so far? Does everybody understand what we've covered so far? Is anyone confused? Does anybody know?
No, I can't see the, yeah, that'll work.
Let me stand on this side first. Okay. All right. So while I'll give you guys a few moments to write this up. So what we're going to talk about next is just some nonlinear models of pair effects, right? Because this assumes that your action is going to depend on the mean. But there are a lot of reasons why we think that your actions might depend not on the mean. For example, let's say you want to get into medical school and you're like, I have to be at the top of my class, right? And in pre-med classes, everybody has that perspective, then you can have a situation where what matters is not the mean, but what matters is where the best person is in the class, right? Or you can have a situation in business school. How many of you guys are thinking about going to business school or law school? Okay. So in a lot of business schools or law schools, you're good as long as you're not in the bottom 10% of your class. And so what can happen is everyone's trying to target not being at the bottom 10%. They want to be at the bottom 15% because you get to have the law degree, but then you get to party or relax or whatever you do during law school. Right? All right. I'm going to continue on with writing out these nonlinear models of pair X. So nonlinear models of pair X. Okay. So the first thing we want to say is that linearity is a strong assumption. So we require students to respond to mean and average actions and attributes of their peers. The second issue is that in a linear model, redistribution always makes one group better off at the expense of another. By redistribution, we mean like redistribution of students, for example. Right? Because if we took like some of the smart students from this class and put them in another class and replace them with like students that were less smart from another class, then it's like that's obviously going to affect the average level of skill that's in this class. But it's going to make the other class better off. So this is one of the reasons why we want to think about nonlinear models. I'm going to write over here. Okay, so what are some examples of nonlinear models? So the first one is the shining light. So the basic idea is one great student can inspire the class. So this would be like in football, right? If you have a Deshaun Watson, it doesn't matter like if everybody's looking around, like he's just going to flip the ball and just go up like that. You just need one star. The second one is called invidious. Let me write this very clearly. Invidious comparison. That clock is right. We have 10 minutes left in the class, right? Yeah? It needs comparison. So like, where high achievers make others feel bad about themselves. Because they push others down in rankings. Green is going to be the boutique model. And so this invidious comparison, for example, would be if you're in a class where there's a curve. Like everybody hates the kids that are breaking the curve, right? I mean, like, especially the kids breaking the curve. It isn't just you're the first ranked person, you're like the first by a standard deviation. And so it's like the second ranked person that gets an E just because you're such a genius. The boutique model. So this is So in this boutique model, students, okay, students have higher achievement when grouped with peers of similar ability. What would be a context where this would be the case? Who here plays sports? Do you like to play with people that are way better than you or that are way worse than you? Better, okay, that's fair enough. But a lot of people like to track. Like if you're too much better than me, then I feel demoralized. If you're too much worse than me, then you're like hitting moon balls at me all day and I'm like, this sucks, right? So you want to match the level. And so students have high achievement when they're grouped with pairs of similar quality. So like high ability kids with high ability kids, low ability kids with low ability kids, because in that context, whoever the teacher is can like focus in on particular students. This is a class where we need to move faster because everybody's fast. So this is a class where everybody's slow. Or can you in the back see up to here? No? Okay. We will continue to smile as you shake your head. Just smile. All right, so we're going to put this up here. Does everybody have that written down? Okay. I want to make sure that I go through that with these and allows people to write effectively. So number 4 is it's called the rainbow model. Okay? And this basically says all students are better off when students of many different achievements are in the same category. And somehow like you learn from each other, you learn from each other differently. So this is all students better off when there are peers of varying abilities. So for example, like what could happen in a case like this is the really smart students can benefit because they're teaching the kids who are less smart and they really like to teach those kids, right? And then the kids who are less bright, they benefit because they're actually getting taught by the smart kids who really enjoy that. And then the kids, I hope I didn't offend you, I'm sorry if what I said is offensive. You're good? All right. It's just that when you're up here and you're looking out into the classroom, like you're taking in like the body language of everybody that's out there. I was at a conference once and there were like 300 or 400 economists there. And this was a really kind of amazing panel of people that I respect a lot. Like some of the key people who do research in education. And they were talking about online education. I really wanted to ask a question because these are the folks that I've admired for a long time. And so everybody's hands are going up and I was like, I know what I'm gonna do, I'm gonna smile. And so I just go up and I put on a big smile. They're like, you over there. Yes. But so it's interesting like how like these like the research shows that like 57% of what you communicate is really your nonverbals in terms of like how you sit, whether you smile. So Amy Cuddy, who's a professor at Harvard Business School, she has this thing where she shows that like if you do power poses, like you tend to be more successful. So like before you go into your interview, like do like the cross leg into like the victory pose, and then you walk in because when you do that, it releases cortisol and like other things that are positive for you. So I'm really big on that. All right, so the rainbow model. So all students are better off when their peers of varying abilities, right? And so you can have a mechanism where there's this kind of a helping that happens. I know for me when I took physics, like I really enjoyed like having students of varying abilities because if I didn't know something, it would help me. If I knew something, I could help somebody else, and I learned a ton by teaching other people too, right? Okay. Number 5, single crossing model. says is that, okay, everyone benefits from having higher ability peers. But high ability students benefit even more. Benefit even more from having high ability peers. So you can think about this as like the Ivy League model, right? Like if you get the absolute best people, or no, the Golden State model, right? It's like Kevin
Kevin Durant?
yeah, the guys before him, Klay Thompson and Steph Curry are even better if you put Kevin Durant there, right? LeBron James is going to be even better if you add Chris Bosh in this. This is like the dream team model. That's exactly what like the single process model. Yeah, exactly. Okay, cool. And then there's one last one that I'm going to put on the board, and it's going to be the bad apple. Who can guess who the bad apple is going to be? Yes.
So like some people are self because one student knows good.
Yeah, exactly. Who's good in a class like that? Well, like one person is like really screwed it up. That raise your hands. But yeah, that's exactly the idea. One rotten apple spoils the batch. So this is the presence of a single or a few bad students bring everyone down. So this is like the class with like the disruptive kid who like pranks the teacher and like is a total disruption, and because of that, the teacher has to leave the room and take the kid to like the principal's office, and it's like this is them like happening. Okay. So these are the different like models, right? And you can see they're all nonlinear in the sense that for this model, you just need one bad kid to mess up everything. For the shining light, you just need one good kid or a few good kids to make everybody like amazing. And so if you have 10 good kids, you want to distribute them. In this context, if you have 10 good kids, you want to distribute them one in each class. In this model, you have 10 bad kids, you want to put them all in the same class so they don't contaminate.